Okay, 6.2. Okay, we start working with volumes. Okay, and volumes.
Professor, we can't see the
Oh, you
screen.
can't see the screen? Okay. Let's see. Can you see it now?
Yes.
Okay, perfect. Thank you. Okay, okay, 6.2 is on volumes. Yeah, I'll change that. Yes, any. Okay, 6.2 is on volumes, the beginning of volumes. Okay. The area of a circle is pi r squared. If we revolve about the x-axis a function of x then f of x is the length of our radii and we obtain a volume of the solid by integrating the integral from a to b of pi f of x squared dx. Okay, where x is going from a to b. Okay, so we say that this is a solid of revolution that we're obtaining, and the volume is equal to, well, I'm going to pull the pi out in front. Okay, pi a to b, okay, of f of x squared dx. Okay, so what is this describing? Well, if we take a function, okay, then we can think of f of x as the height of this function at any value x, right? It's the height of that function. Okay, and so if I revolve it around the x-axis, I get a bunch of varying circles, okay? A bunch of varying circles. And when I sum all of those circles up with their various radii, I will get the volume of the solid of revolution. Okay, and so the f of x is just my varying radius lengths. Okay, because however far I am from the x-axis is the height of my function, but that's just the y value. The y value at that value of x is f of x. Okay, and so it tells me that radius for that slice okay, that slice of the volume is gonna be pi r squared at that, for this specific slice, and then what I do is I just sum up all of the slices, the infinite slices, I sum them all up using integration. Okay. Okay, let's do an example. Number one, find the volume of the solid by rotating about the x-axis the region under the curve y equals radical x from 0 to 1. Okay. Okay, so what does this guy look like? Y equals radical x. Okay, looks like this, from 0 to 1. Okay, it goes through 0, 0, and it goes through 1, 1. And so I'm gonna revolve this about the x-axis. Right? And so I get my various slices. Okay. And then I'm gonna sum all those slices up with my varying radii. Okay. And so I want this volume here, this total volume. Okay. And so, well, how do we do that? Well, the volume is going to be equal to the integral along the x direction from 0 to 1 of, and I have the pi in front, it's pi times the integral from 0 to 1, okay, of f of x squared. Okay, so that's radical x squared. Easy. Okay, don't want to scare you right out of the bat, right out of the gate, that, with hard integrals, they get plenty scary pretty quick. So we'll start off with an easy one. Kind of lob one out to you. Okay, so pi times 0 to 1 of radical x squared is just x dx. Okay, so this is going to be equal to pi times x squared over 2, 0 to 1. Okay, so this is pi times 1 squared over 2 minus 0 squared over 2. Okay, that goes to 0. That's 1/2. That's pi over 2. Okay, so that's the volume of the solid of revolution. Okay. Okay, so this is if we revolve around the x-axis. What happens if we revolve around the y-axis? Okay, well, to revolve around the y-axis, we solve the function for x which gives us x of y, or sorry, f of y, which is our radius. It's our new radius. Okay, and the volume of the solid is found by integrating v equals c to d of pi times f of y squared dy. Okay, so now we just have a y-oriented function. Okay, and that's going to be our radius. Okay, so number 2, example 2, says find the volume of the solid obtained by rotating y equals the square root of x about the y-axis from 0 to 1. Okay. Okay, so in this case, okay, we still have our y equals radical x, okay? But in this case, y is going from 0 to 1. So 0 is less than or equal to y is less than 1. So y is going from 0 to 1. So where are we revolving this? We're revolving it around the y-axis this time. And so what's the radius? The radius is going to be this little slice here. Okay, and we're going to revolve, oops, like so. I draw it a little bit better. Not like that circle. Right? We get that area or that volume now. Okay, instead of the other one. The other one we kind of got a cup. This one looks like kind of like a spinning top. Okay, so they are different volumes. Okay, they're going to be different volumes. You know, one's kind of like a cup on its side, and this is like a spinning top. Okay, but what do we have to do? We have to put this in terms of y. Okay, so I'm going to take y equals radical x, and I'm going to square both sides. And so I get x is equal to y squared. Okay, so f of y is equal to y squared. Okay, so what's our volume going to be? It's going to be pi times the integral of still 0 to 1, because y is going from 0 to 1, of f of y squared. So this is y squared squared dy. Okay, which again is not a real tough integral. 0 to 1 of y to the 4th dy, which is equal to pi times y to the 5th over 5 from 0 to 1. Okay, and we plug 1 and 0 in. Pi times y 1 to the 5th over 5 minus 0 to the 5th over 5. And so this becomes, this goes to 0, 1/5 times pi is just pi over 5. So whereas the cup had a volume of pi over 2, this top, spinning top, has a volume of pi over 5. Okay, smaller volume. Kind of makes sense if you look at the diagrams. You know, this has much more girth to it and a bigger volume, and this one has a less volume. Okay, so this method that we're talking about, this kind of like pi r squared method, okay, or Okay, this can sometimes be called the disk method. Because what you're doing is you're taking a function and you're summing up an infinite number of disks. Okay, in order to get the volume. Okay, so we call that the disk method. Okay. Okay. The next method is called the washer method. It's basically the disk method, but we're punching out. If you look at a washer, right? A washer is not a disk. This is a disk. A washer is a disk with a hole in it. Okay, this is a washer. So what happens is we end up with two functions. Okay, we have maybe an f of x function and a g of x function. Okay, and we're really interested in just the area between them rotated 360 degrees. Okay, and so this creates, okay, a hole, okay, in our disks. And so this is called the washer method. Okay, so let's do an example of how we would get the washer method. Okay. So if it's an x-oriented function, okay, an f of x and a g of x, then it would just, the formula would look like this. Pi a to b of f of x squared minus g of x squared dx. Okay, this is the washer method. Okay, because basically what we're doing is we're finding an area, or we're finding a volume, okay, the volume for f of x, and we're subtracting off the volume for g of x. Basically, creating, this donut, okay, that we take the volume of the larger function and we subtract off the volume of the smaller function. Okay, very similar to what we did for areas between two curves in the previous sections, but now they're squared because they're not areas, they're volumes now. Okay, and their f of x has a radius and g of x has a radius. So I mean, my diagrams aren't as good as the ones in the book, but they'll suffice. Okay, just think of it like this. Okay, I'll try to make it a little bit better. Okay, so think of it as we had, some function that goes like that. Okay. Oops. Okay, maybe oops, the opposite. Okay, and then we have another function. Maybe this function goes like so. Okay. Okay, so we end up like that. Okay, and what we're really interested is in the volume. Okay, this total volume around the figure. Okay, but the volume is going to have a hole in it. Okay. Okay, that volume, it's going to have a hole in the volume. Okay, depending upon what the nature of the functions are. Okay. Again, my 3D models aren't really that good, but if you wanted to Okay, just color the whole thing. Whatever. Okay, it's just this has a hole in it. Okay, maybe I should use different colors. Bloop, bloop, hole. Okay, this is covered because it's the whole volume, but whatever. Again, my attempt at 3D modeling. Okay, but here's the formula. Okay, here's the formula. Okay. Number 3. Okay, find the volume out of the solid obtained by the region enclosed by y equals x and y equals x squared about the x-axis. Okay. Okay, so what is this going to look like? Draw a picture. We have y equals x, which is just my 45-degree angle. Okay, that line there. And then I have y equals x squared. What's that? That's just my parent function parabola. It's just my run-of-the-mill parabola. But what happens? Well, it intersects. It intersects where? It intersects at 0 and 1. And I get this nice little, I'll zoom in. I get this nice little area in between. Okay. And if I were to revolve this about the x-axis, I don't like that. Let me draw the, do this. Let's do a mirror image. As close to a mirror image as I can get. Okay, and then down there, okay, we get that as our other area. Okay, now we'll draw our circle. Okay, now it's looking nice, a little nicer. Okay, and so that's our volume. Okay. I don't want to fill it in because then we're going to lose our voluminess. Okay, but just know that we have this inner gap that is empty, and then we have an outer gap of our that's going to create our washer. Well, I don't like that. Let me try to make that circle better. The inner circle I liked. The outer circle not so much. Do the outer circle here. This is my washer. That's a better outer circle. And so what's the volume that's going to be created? It's going to be around these washers. Okay. So we're taking that inner circle, we're punching out, or we're taking the outer circle, we're punching out the inner circle, the inner volume. We're taking the outer volume, we're punching out the inner volume, and getting the exact volume. Okay. So how do we do this? Well, it's pi times the integral from where? Well, where is it enclosed? Where is it enclosed? It's enclosed from x. X is 0 to x is 1. So x equals 0 from 0 to 1. Okay. And then which one's on top? What's my top function? What's my f of x here?
Y equal X.
Yes. Thank you. Thank you, Con. Very good. Okay, yes, the top function is y equals x. Okay, the bottom function is y equals x squared. So this is gonna become x squared minus x squared squared dx. Okay, so we get pi times 0 to 1 of x squared minus x to the 4th dx. This becomes x cubed over 3 minus x to the 5th over 5. From 0 to 1 times pi. I'll give you a minute to write that down. I wrote that rather fast. Okay, so when I plug in 0,